All right, so welcome back. We're into our lesson on torque, and torque is essentially the analogous concept to force. So when we talked about force as a push or a pull that caused some sort of acceleration, torque is the effect of a force acting at a distance to cause something to rotate or change its rotational acceleration. So, just coming back to an idea that we talked about in force and Newton's laws was equilibrium. So, equilibrium occurs when things are balanced. So, to achieve equilibrium, you have to satisfy two conditions. You have to satisfy the condition that all the forces balance out, so the net force is zero. And then the other part is that all the torques balance out, or the net torque on the system is also zero. And we've talked about different ways that you can have equilibrium. So we had static equilibrium when it was stationary, so there was no acceleration whatsoever. So there's no motion if it's static. And then dynamic equilibrium is when something is moving or rotating at a constant velocity. So it's got a constant rotational velocity or a constant linear velocity. Translational is just a fancy word for linear. Static means it's not rotating, it's not moving. So again, torque is the rotational analogy or analogous to force. So this example is a good kind of concept to help you with torque. So if you imagine a door or a beam, so this board is like our door, or the hinges of the door are on this side, where it's going to rotate around, and your doorknob or handle is on this side. So the ideas that create torque you are familiar with from your everyday experience. So when you open a door, you're creating a torque. So you push or pull at one end, it rotates at the other end. The amount of force you apply, that's F. R, which is something known as the lever arm, is the distance from the point of rotation to where you apply the force. And then those two combinations, and then there's also the factor of the angle that you apply it at. So those things impact the amount of torque. So we'll get to the equation in a second. But this door is rotating if we pulled on it or pushed on it this way, and this is the hinge. The door is going to rotate that way, and then the torque is actually into the screen. We'll talk about that with that right-hand rule again. So you curl your fingers in the direction of the rotation. Your thumb points in the direction of the vector. So the rotational vector is going into the screen. So to calculate torque using R and F and the angle theta, you just have to multiply. So you're multiplying R, which is that moment arm or lever arm. It's the distance from the point of rotation, the hinge, to where the force is applied. F, which is the amount of force that you're applying. And then theta is the angle between the lever arm and where that points and the force. So in this one, it would be that angle theta. So theta is an angle. Lots of times, if you look at this, to maximize your torque, you will push, you want to make an angle that would make this as big as possible. So that angle is 90 degrees. So if you put sine of 90 in your calculator, you should get 1. And that's the maximum value for the sine function, which will make torque the largest. The unit for torque, R is measured in meters, and F is measured in newtons. So meter newtons is our measurement for torque. It can be positive or negative, just kind of basic ideas. The way that we establish positive and negative rotation, I think I might have skipped over this, so I'll come back to it. If you're labeling your axes with degrees, this would be like 0 degrees, 90 degrees, 180, 270, and eventually we come back and we get back to 360. Going around the circle in that direction is the positive direction. So in math class, they established if you go this way around the circle, that is the positive direction. So anything that is counterclockwise is that direction. So that's the opposite way to the way the hands of a clock move. That's positive. And then negative would be going the opposite way. So if we went 0 to here, that'd be like negative 90, negative 180, negative 270, and then finally negative 360. So those degrees, again, going around that way, that's the negative direction. So negative is clockwise. Sorry, I wrote CW up there for clockwise, but it should be counterclockwise is positive. So positive direction in rotation, and for torques, we're going to have as counterclockwise, following the circle going around, just follow your degrees. And then negative would be clockwise. So just making sure you are aware of that. All right. And I think I jumped the gun here. So torques measured in meter newtons, we did that unit, has a direction. We use the right-hand rule. So we can use the right-hand rule and use our thumb for the direction. Or if we're just talking about clockwise and counterclockwise torques, that's fine. So our first situation here that I want you to think about is we have this board. The point of rotation is here, this black dot, and we are going to apply these different forces on the board, force A, force B, force C, force D. You can read their amounts, and they're applied at these positions as shown in the picture, and we're trying to determine which of these forces, A, B, C, or D, is going to create the greatest amount of torque. And then we're going to rank them from the greatest amount of torque to the smallest. So, and then we're supposed to explain our reasoning. So let me give you a second to kind of consider that and think through what you might have for an instinct. You don't have to really do the math here, you just have to think about the concepts. So remembering the equation would probably be helpful. So let me see if I think I have the equation right under here. Yep. So torque, which is again that symbol tau, is equal to RF sine theta. So again, R is that lever arm, it's the distance from the point of rotation to where the force is. F is the amount of force, sine, and then theta will determine that portion of it. So if we just go through them, if we look at A, it's 1,000 newtons for the force. This force is at 90 degrees because but the lever arm is nothing. So if you have 0 for your lever arm, you're going to get 0 torque. So that's not going to produce any torque. It's like pushing at the hinge. You can't open the door if you just push at the hinge. The other one that's going to get you 0 is D. So D, it's 800 newtons of force, but it's applied kind of, if you look at these two directions, R is going out this way towards the force, and then that force is pointing back the opposite way. So that angle between those two is 180 degrees. And if you put sine of 180 in your calculator, that's supposed to be an 8. If you put sine of 180 in your calculator, you get 0. So both those two are 0 for those reasons. And then the other two, they are actually also, they're both going to produce torques. They have the same amount of force, but what's different about them is where they are located. So this R value is going to be different. And the bigger the R value, the further you are away from the point of rotation, the bigger the torque you produce. So C is going to be the biggest because it's at the entire length of the board. And B is only at half that length, it appears. So I would say C is the biggest torque, then followed by B, and then A and D don't produce any torque, so they're the same down here at the smallest end. All right. We're also going to be able to apply those same concepts with equations to calculate different values. So if you look at this situation, it says, what must this force be being pulled here to achieve equilibrium? So again, with equilibrium, you have all the forces canceling out, and you have all the torques canceling out. So we're really looking at the torques canceling out here. I've drawn in some pictures. So there's this block here. If you imagine this is sort of like an Atwood machine, which we studied. This block is trying to pull down with this string at this position. So I just call that torque from the 10 kilogram block. If I imagine that as the only thing, it would rotate in the counterclockwise direction, which is the positive direction. If I look at torque 2, it's going to go the other way from this 2 kilogram block. It's pulling down here, so it's going to rotate the wheel in that direction if it was the only force. So that torque is a negative torque. And then the force that is applied here that we're trying to solve for is pulling in the same direction as torque 2. So those two are pulling in the clockwise direction. This one in red is going in the counterclockwise, and they should balance out and go to 0 if we do that properly and solve it correctly. So again, the torque should be 0. I did the individual amounts from this RF sine theta equation. So just reading through these are in centimeters, so you got to divide them by 100. So for the 10, it's starting here. So that's the 2, that's the smaller wheel. That's 0.02 for the radius, or R. 10 is the amount of the mass, and 9.8 is the acceleration due to gravity. So the weight of this block is pulling, so that's why that's the force of gravity equation. And then it's at 90 degrees. So the force of gravity is down, and the wheel is set up so that this is perpendicular, this radii, or this R vector. So if you do that, you get 1.96 meters, and that's in the positive direction. We repeat the same process just with 0.03, because this 2 kilogram is at the larger radii for this wheel. So it's 0.03, it's 2, 9.8. Again, it's sine of 90, so I didn't bother with that part. And it's negative this time, so that's a negative 0.588. And then we have this other force that's going the same way in that negative direction. So when we add those two together, they should cancel out that one. And that's what I hit over here. So when I add all these together, the torque from the 10, the torque of the 2, and the torque of F should add to 0. So I solved for torque F and brought it over to the other side and made it negative. When I put the values in that I got over here, 1.96 plus a negative 0.98, I get negative 1.372 for my torque. And then that I have to solve for F, so I'm going to divide by the radius that it is away. So this is the bigger wheel again, so that's the 0.03. And if you do that properly, you should get 45.73 newtons. So again, hopefully not too confusing, just using this equation and this idea with equilibrium to try to figure out a force. There is also another way that we can look at forces. So that was sort of the kind of chart method where you add up all the forces, you get the net force. Newton's second law, which was F equals ma, that still applies for rotating bodies as well. We have different letters because we don't use force and mass and acceleration. We use torque. So again, this is just kind of like translating an equation into a different language. So we have torque for the force. We have alpha for the angular acceleration, which we learned about last lesson. And then for mass, we have something called rotational mass or rotational inertia, or another name for it is the moment of inertia. So there's a couple different synonyms for it. So I, this letter I, is the rotational inertia, and we're going to talk about that next. But it's just the same idea of the force applied is equal to the mass times the acceleration, or the torque applied is equal to the rotational inertia times the acceleration that you're encountering. So either of those kind of concepts, it's still the same equation. It's just, you have this new concept of I. So we're going to talk about that. So rotational inertia is, or moment of inertia is I, and it's the analogy to mass. So it's not exactly like mass, but it's the same. It serves the same purpose. So just like mass, the greater the inertia, the more difficult it is to change the object's motion. So, a bigger object's harder to accelerate. A body with a greater rotational inertia is harder to rotate. So it's the same concept. It just has another factor in it. So to determine the moment of inertia for an object, the mass of the object and the distance from the mass to the axis of rotation must be known. So again, r is that distance from the point of rotation to something. So in the last equation for torque, it was from the point of rotation to the force. In this equation, it's from the point of rotation, or where those things are rotating around, to where the masses are. So if you just have a point, like a particular point mass, then you just do mr squared. If you have many points, like we're going to do an equation or a problem with that in a second, you would have the mass at some position squared plus another mass at a position squared. So again, sigma means you just add up. So you would find each individual mass at its individual location squared away from the point of rotation, and then you would add all of them together. That seems rather complicated once you get to a body that has continuous mass through it. So if we imagine a wheel or a disc or something that's rotating, and it's a solid body, there's lots of masses at different points. So it would be kind of complicated to do that. So you won't have to do this equation. I will tell you any of them that you should know. And I have them on the next slide. But in calculus, if you had calculus, you would integrate and you would find it. That's how you would go about it. So just coming back to this formula, though, this is like the generic formula for a particular point or collection of points. If you want to increase the moment of inertia, what would you do to the mass? So if you look at this equation, mass is in the same part as I, so that's a direct relationship. So if you wanted to increase the mass, or if you increase the mass, that's going to cause an increase in the moment of inertia. So the more massive you are, the harder it is to get it to rotate. That makes sense. The other idea is, what would you do to the distance? So what would you do to r? So if you look at r compared to I in the formula, again, they are in the same position. So if you increase the distance away, it is harder to rotate. So some examples of this that make sense, I think, are if you imagine an ice skater, so an ice skater spinning. So if this is my stick figure ice skater, and let's say they're spinning around their body and there's some axis of rotation going through their body, so like vertically this way. So when they're skating and they're spinning, if they are going slow, you notice usually their arms are out. What happens when they tuck their arms in? So if they go from that to a shape more like this, where they tuck their arms inward, what happens to their rotational rate? And if you think about that, they go faster. So like they're still rotating around the vertical axis, but they've brought their mass inward. So their mass is further out here on the ends of their hands. And by bringing their mass in towards their center, they've reduced their rotational inertia and they speed up. So they go faster. Another example of this is if you ever played softball or baseball, it's choking up on a baseball bat. So like if you have the bat here, if this is like a bat, and I haven't done a very good job, but here we go. That's a little bit better. So if you think about the point of rotation, it's wherever you put your hand. So if you're holding kind of the end of the bat here, that would be that. The mass of the bat is mostly concentrated in the head. So like that distance from there to there, that's R. If you choke up on the bat, you're actually moving your hands further up the handle. So you put your hands here, that R value has decreased. And if you decrease R, you decrease I, and that makes it easier to rotate. So that's why your coach told you to choke up on the bat if you need to swing the bat through the zone quicker. So that's a, an example that hopefully makes sense. The ice skater also is another one that I think makes sense logically to people, and that makes sense. So so the closer the mass is to the point of rotation, the easier it is to turn, and the further it is away, the harder it is. And that's, again, just based on that equation. So we're going to look at these two collections of particles. So there's two masses, one is 5 and one is 7, and they are located some distance away from an axis of rotation. So this whole distance between them is 4. So if it's halfway, that would be 2 to the 5, and it would also be 2 to the 7. Same masses, they're still 4 away, but now we've changed the point of rotation and where it's at. So we've moved this axis of rotation over to this left side, and this is 0.5 away. So if you measure from that axis to the 7, it's going to be 4.5 away. So just looking at those and thinking about the ideas that we talked about, which one do you think is going to have more difficulty rotating? So essentially, it's the same amount of mass, but they're located at different points. I would think that we said that if you increase the distance away, then you're increasing the moment of inertia. So B should be the one with a greater moment of inertia or rotational inertia or rotational mass. All those ideas are the same. So let's go ahead and calculate them. So for each one of these points, we're going to do I equals mr squared. So by doing the first one, it'd be 5 times 2 squared plus 7 times 2 squared. 2 squared is 4, 4 times 5 is 20, and then 2 squared is 4, and 4 times 7 is 28. When we add those together, we get 48 kilogram meter squared. That's the unit for it. That's the rotational inertia of this configuration about this point of rotation or this axis of rotation. When we do the same math for these distances, however, it gets much bigger. So 5.5 squared, that actually is a lower amount because you've moved the 5 closer to the point of rotation, so that's only 1.25. But you've taken this 7 and you've moved it a significant amount away. You've more than doubled it, and it's the squared of that. So it's 7 times 4.5 squared. That gets you 141.75. You add those together, you get 143. So 143 is larger than 48, so this one is harder to rotate, which is what we said should make sense in our situation because we've moved more of the mass away. All right. Here is the slide with all of the different shapes that might be rotating around different axes that we would work with. Again, you don't have to memorize this or be able to calculate kind of these ideas or come up with these equations. You just have to use them. So based on what you're given, I think we're going to use a solid cylinder later. So we're going to use 1/2 mr squared when we get to that, like a disc or cylinder. And you just have to be able to plug in for the amount. So 1/2 m is the mass of the disc, and then r would be the radius of that disc, and you would square it. So you just use whatever the concept is and work through there. But you shouldn't have to worry about it too much. All right. Oh, sorry. Came up with some news. So for this problem, it says a wheel, and it tells you the radius, and it tells you actually the rotational inertia. It says is at rest on a fixed axis, and then a force of 0.45 newtons is applied tangent to the rim of the wheel for a total of 5 seconds, and we want to figure out what's the angular velocity of the wheel after that time. So this is rotational kinematics and our torque idea in one problem, so that's not bad. So I started out with like what was given. So in the problem, it told us lots of information. It told us the radius of the wheel. It told us the moment of inertia of the wheel. It said that it was originally at rest, so omega I is 0. It told us the force that's being applied and the time that it's being applied for. So those are all the things that are given. And I drew a picture of what's kind of happening. So there's this wheel, if it's rotating around its center, we're applying a force and it's going to start spinning, and it didn't say direction, so I just had it going that way. So what we need to do is we need to solve for, okay, what do I have? I have F and I have R, so I can figure out how much torque is being applied. Once I get the torque, then I can use that with the I value to maybe get the acceleration, and then once I have the acceleration, I can use kinematics to get to what is the final speed after some time. So I wrote it out here. So torque equals RF sine theta. So 0.25 is the radius, 0.45 is the force, sine of 90 because it says it's tangent to the circle. So it's tangent to the circle, it's only touching at one point. You're always tangent at a radius there. So that's 90 degrees. And then that's equal to I alpha. So it's just the torque equation, both torque equations in the same problem. So I is 0.0625, and then alpha is what we're going to solve for. So if you solve for alpha, you get 1.8, and then it just becomes a kinematics problem. So in the kinematics problem, you go to the chart, just like we did in the past. So delta theta, we didn't tell anything about it, didn't ask us, so that's going to be the equation that we want that doesn't have delta theta. The initial velocity was 0. The final velocity is what we're solving for. We know the acceleration is 1.8, and we know the time is 5. So plugging into that formula, omega F equals omega I plus alpha T, we solve and we get 9 radians per second. So that's the speed of the wheel at the end of that 5-second interval. So we'll keep it moving. There's another problem or two here, and then we're about done. So just kind of making sure you've seen a couple of problems. So this one, it says 2 children push on opposite sides of a door. And they both push horizontally and perpendicular to the door. One child pushes with a force of 165 newtons at a distance of 0.6 from the hinge, and the other child pushes at 0.4. And we want to know how hard does this second child have to push in order to keep the door from moving. So the door is not moving, it's in equilibrium, so the net torque is 0. I believe I drew a picture here. Yep. So I drew a picture with the concept. So I have this first child pushing to the right with 165 at this distance of 0.6 from the hinge, and they're going to try to get the door to rotate in the clockwise direction. The other child has to push the opposite way, and they're pushing at 0.4, so they're closer, and they're trying to make it rotate the opposite way. Because they are closer, their lever arm is not as big, so they have to push with a bigger force. So I would expect the force 2 to be bigger than 165. And again, it's just doing the two torques added together equals 0. So torque 1 plus torque 2 equals 0. For torque 1, they're both 90 degrees again, so it's negative for this one because it's going clockwise. 0.6 times 165, and that's plus 0.4 times F2, and we get 0. So I'm going to move that to the other side. It becomes positive. So I have 0.4 F2 equals 99 divided by 0.4, and you get 247.5 newtons. So that's how much force F2 has to be, and we said that makes sense because they're closer. So if you're further away and you apply a force, to get the same amount of force at a closer, or same amount of torque at a closer distance, you'd have to push with more force. Okay. The last one here, another one, it says, suppose you exert a force of 212 newtons at a radius of 0.235 meters on a grindstone. So this is the one that we're going to figure out I. So 75 kilograms is the mass of the grindstone. It's a solid disc, so for a disc, it's 1/2 mr squared. So 1/2, 75, and then the 0.235 meters is the radius. So I square that. You get 2.07. And I forgot to cover things up, or maybe I did. And we're going to solve for the torque again. So torque would be the force times the lever arm times the sine, and it says tangential again, so that's fine. So RF sine theta, that's a theta there, even though it looks like a 0, that's supposed to be a theta. There. And so it would be sine of 90. You get 49.82 meter newtons for the torque. And then once the angular acceleration, so we're going to take this number and divide it by this 2.07, or the alpha, using Newton's second law for rotating bodies. So 49.82 divided by 2.07 gets you the answer here, which is 24.07 rads per second squared. So that is the lesson for today on torque and rotational equilibrium and moment of inertia. So hopefully that makes sense, and I will see you in class. Have a good one.